All right, good morning. Let's get started. So I'm collecting homework 4A from you now, and homework 4B is due in a week. There's only 4 problems on that assignment, and it's because they're a little bit more lengthy. It's not going to be over-the-top kind of crazy stuff. We're doing a couple of problems today. I have an in-class exercise I'm going to hand out and collect for a small number of homework points. That I hope, working through that in class while we're all together, will make working on the homework assignment that much easier. So today we're going to be talking about Euler's equation. And last time we had a very brief taste of the kinds of problems that Euler's equation is equipped to handle by looking at the very simplified situation of what if liquid is accelerated in the same direction as gravity. And sort of the simplistic way that we handled that problem is going to be replaced today by something a lot more robust. Euler's equation answers the question, what is the pressure in response to local acceleration? And it's also not just the pressure, but also changes in liquid elevation that can be affected by local acceleration. So this is the form of Euler's equation that would be on an equation sheet I'd provide. But it requires a little bit of massaging and transformation into something useful before you can start substituting variables into it. And so probably the most common mistake I see from students during exams, particularly students who didn't really understand the assignments before they turned it in, is they just start substituting numbers directly into this formula. And it won't work. It'll never work. What you have to do is you have to consider what is the direction of acceleration, for one thing. You'll notice here in Euler's equation, it's saying acceleration in the L direction. Well, usually Euler's equation problems, we're going to be applying these in 2 directions. We'll be considering the horizontal movement of a liquid and then also whether or not it has vertical movement. We won't consider or apply Euler's equation in 3 dimensions simultaneously, although it would work out just fine if we did. And so when we apply Euler's equation, if there is acceleration at the same time in 2 different directions, that means that we have to apply Euler's equation one direction at a time. And that's the first thing I'll say about it. The next is that you'll notice this negative sign here. And this comes from a really important concept that pressure increases in the opposite direction of acceleration. And so take, for instance, if we have an enclosed tank of water and we accelerate it to the left. What that means is that the pressure will build up on the right side of the tank. And so the pressure increases in the opposite direction of acceleration. If we accelerate upward, the pressure increases downward. So the pressure on the bottoms of our feet is what we'll feel as the result of that acceleration. So that's sort of the origin of this negative sign. And then inside of these brackets is what's affected by the fluid acceleration. It's the piezometric pressure. So P plus gamma Z is the expression we've seen before when we've talked about piezometric pressure. And what it means is that the fluid may have its pressure changed as a result of acceleration, or it could be Z, which is the elevation of fluid, or its position. So let's say, for instance, that we have acceleration in the x direction. So what we can do is, first of all, transform Euler's equation from partial differentials to just saying, let's consider a change. This delta means the change in pressure plus gamma Z relative to some distance in some change in distance in the x direction. So 2 points are going to be some distance delta x apart. And so here now I've broken this up into saying, instead of a change in pressure plus gamma Z, let's look at the piezometric pressure at 2 and the piezometric pressure at 1, where those are 2 different locations that we're going to be comparing how the pressure plus gamma Z has been affected by the acceleration of the fluid. You also notice that the density of the fluid is a part of Euler's equation, because the more dense the fluid, the greater the effect will be when that fluid is accelerated. In the same way that when we go downward through a liquid, the pressure increase is greater for a dense fluid than if we're going downward through a fluid with a lower density. And so if we go down 1 meter through a very light oil, then the pressure increase is less than if you go down 1 meters in depth through something very dense like mercury. So location 2 and location 1, we're going to have to be very careful about how we consider our general assumption, sort of our directions that we're going to say is the standard convention is that whatever location is further to the right is we're going to, in the x direction, assign that location 2. And whatever has the most elevation when we're considering acceleration in the vertical direction will be location 2. So you'll notice that this equation has been written with delta x and acceleration in the x direction. We could write the same equation, and if we had acceleration that was up or down, we would simply replace the x with z to indicate vertical, and then it would be acceleration in the z direction. And so this same Euler's equation can be applied whether it's side to side or up and down. And it's simultaneously accounting for the natural effects of the hydrostatic equation. The hydrostatic equation is built into this, so that even if there's no additional acceleration beyond ordinary gravity, Euler's equation would still be able to tell you what's the pressure change between 2 points. So we don't have to separately account for this hydrostatic effect. It's built in the hydrostatic equation and also the effects of movement in whatever direction we're applying this to. All right, so just as a first chance for you to see the effects of Euler's equation, let's consider this, this truck, which is moving, and it's accelerating to the left. It says in this problem statement that it's slowing down at a rate of 3.05 meters per second squared. So it's moving to the right, and since it's slowing down, that means the acceleration is to the left. Now we have to be really careful, since we assumed that positive x direction is to the right. When we substitute the acceleration into Euler's equation, we would use negative 3.05 as our acceleration, because its acceleration is to the left rather than to the right. Now, I'm not sure why a box truck like this would be carrying gasoline, but that's the example, is that the fluid inside here has a unit weight of 6.60 kilonewtons per cubic meter, and then to make things even more perplexing, it's open to the atmosphere, like it's vented there at location T. So the pressure there is 0. There's just a small opening. And so that, knowing the pressure there is going to allow us to calculate the pressure at other locations because of the acceleration of this truck. Now, it's enclosed. The fluid is confined. And so there isn't going to be any change in elevation of this fluid, but the pressures are going to change as a result of the motion. I see the... Well, it sure could. Thank you. There's no air inside of there, but I guess if it's slowing down right now to the left, if it was accelerating to the right, then maybe the gasoline would spill out the back, right? But we're going to focus mainly on how Euler's equation tells us, number one, what's the pressure at A, and then number two, we'll try and investigate where is the greatest pressure in this case. All right, so let me see if I can freeze that. Okay, so I'm going to work through this one on the board. And what we're going to start with is just a little sketch that represents the part of the truck that I'm carrying about, which is where the liquid is. So we've got a rectangle that is 6.1 meters wide, and it has a height of 1.83 meters. And it's full of some liquid that has a unit weight of 6,600 newtons per meter cubed. And then here, the pressure at T is 0. And we're calling this location A. And this is location B, down in the lower right. We can just get some preliminary stuff out of the way. For instance, we know from Euler's equation that we're going to have to know the density of the fluid. And we're given the unit weight to begin with. So let me calculate the density. Density is unit weight divided by G. So 6,600 newtons per meter cubed divided by 9.81 meters per second squared. So that tells me the density of the fluid is 672.8 kilograms per cubic meter. Also, I'm going to interpret the acceleration statement here. So acceleration in the x direction is negative 3.05 meters per second squared. And that's because we say by convention, positive x is to the right and positive z is up. And this acceleration is to the left, and that's why it's a negative 3.05 meters per second squared. Okay, here is Euler's equation, and I want to apply it in the x direction because that is where the motion is occurring. And so my first step of applying Euler's equation in the x direction is to say, well, we're going to look at a change in pressure plus gamma z relative to some increment distance delta x, and that's equal to density and acceleration in the x direction. And you'll note the negative sign that right now is on the left side of the equation. Well, I'm going to apply this by looking at two different points. First of all, in section 1 of this example, it says, what's the pressure at point A? So I need to figure out what's going to be location 1 and what's location 2 when I start substituting, because when I sort of expand out Euler's equation, it's pressure plus gamma z at location 2 minus pressure plus gamma z at location 1 is equal to negative delta x density acceleration in the x direction. So I moved the negative sign over to the right-hand side of the equation and also the delta x. So it's the piezometric pressure at 2 minus the piezometric pressure at 1 is equal to negative delta x density acceleration in x. All right, so look at this picture. Do you remember the rule for what we label as location 2 and what we label as location 1? Whatever's furthest to the right is going to be the one that's location 2. And so A is 2, and I'm going to write this on the board. Never make the step without labeling it, just so that you can keep it all straight. So A is what we're going to call 2, and location T is what I'm going to call 1, since A is to the right, T is to the left. Some other stuff I know, that the pressure at T is 0, and the pressure at A is really what I'm going after here. That's the unknown. If we look at this equation, we're also going to have to account for Z at the locations. And so the Z at location T versus the Z at location A. And so the last sort of preliminary thing I'll say is that those are on the same elevation, so Z sub T is equal to Z sub A. Is there a question in the back? Go ahead.
Does it matter like the direction of traveling?
The direction of acceleration matters, but you always have to assume by convention that location 2 is whatever is on the right side of the 2 points that you're interested in, and location 1 is on the left side of the 2 points that you're interested in, assuming that it's the x direction we're talking about. Later I have an example for you where a container like this is actually simultaneously accelerating in 2 directions. And so I'll show you how to handle it when it's accelerating to the right and also downward. So I think you'll get a better feel for what the rules are there. Okay, so we have the pressure at A plus gamma ZA minus the pressure at T minus gamma Z sub T is equal to negative delta X density acceleration in X. So here I'm just replacing the variables 2 and 1 with the location, with the labels from the drawing. So I'm substituting in A for location 2 and T for location 1. Yeah, they're equal to each other, right. And so what that allows us to do is it allows us to cancel that out. So Z sub A and Z sub T are canceled out because they're equal. And we also know that the pressure at 1, which is the pressure T, so P sub T is also 0. So we can take that out of the equation as well. So what we're left with, the pressure at A is simply going to be negative delta X density and acceleration in X. Okay, now we can start substituting in the actual values. So negative, and now the distance between the 2 points, between A and T, is 6.1 meters. The density of the fluid is 672.8 kilograms per meter cubed. And then the acceleration, we have to be very careful to put in a negative value there since it's accelerating to the left. So we've got the distance, the density, and the acceleration. So the pressure at A will be 12,517 pascals. And hopefully you can sort of visualize or conceptualize of the fact that the pressure at A is going to be high because it's decelerating. Think about if this wasn't enclosed, like if it was an open tank, the liquid would be sloshing to the right side as it slows down. I mean, if you've ever braked really hard, you sort of know everything in the vehicle slides forward, right? So the liquid here isn't moving because it's confined, but the pressure is building up in the direction towards the right because the acceleration is to the left. So again, the general rule is that the pressure increases in the opposite direction of the acceleration, and the acceleration is to the left, so the pressure is increasing towards the right. So that tells us the pressure at point A. Now here in part 2 of the example, we're going to consider where is the pressure the greatest. And so we already know that the pressure is increasing as you go in the rightward direction. And so the farthest right we can get is along that wall AB. Now, hopefully by inspection and just by instinct, you also know that the pressure at B is going to be greater than the pressure at A because it's down deeper into the liquid. And so we're going to say pressure at B is greatest. And now let's calculate what it is. We have two options. When you're applying Euler's equation, you should pick as one of the locations where you actually know the pressure. Where you know something, like where you know the elevation, where you know the pressure. Identifying where the 2 points are going to be, you should try and make it as simple as possible for yourself. So we could use location A as one of the points and then work towards the unknown. So pressure at B would be the unknown. Or we can use the pressure at T as the thing that we know. And the illustration I'm going to show is just let's use location T as the place where we know the pressure and the elevation. But you could get the correct answer by working from A as well. So in this example, we're going to say T is 1 and B is 2. Simply because the acceleration, remember, is along the horizontal axis. So in the x direction, B is further to the right. And this is another point of occasional confusion and mistake for students, is they're thinking, well, location T is higher, so shouldn't that be 2 compared to B? But our acceleration is side to side here. It's not up and down. Although, of course, gravity still applies here. This truck is driving down the road. It's not floating through outer space. So even though gravity applies, location B still is further to the right than location T. So that's why I've said T is 1 and B is 2. So I'm going to write Euler's equation, the expanded out version of it again. So in terms of B and T, it's going to be the pressure at B plus gamma Z sub B minus the pressure at T minus gamma Z sub T is equal to negative delta X, density, and acceleration in X. So let me just point out that, this minus P sub T and then minus gamma Z sub T is simply because here the minus sign applies to both terms inside the parentheses. So we have to be careful to have the minus sign for both of those. Okay, so what do we know? We know delta X. The distance between them is 6.1 meters. We know the acceleration in X is negative 3.05 meters per second squared. We know the density from before, which we calculated, is 672.8 kilograms per cubic meter. Elevations. Let's call Z sub B, let's call that 0 meters of elevation. So that's our datum, our vertical datum. And then we'll say Z sub T, therefore, is 1.83 meters. Is everybody with me on that one? I mean, we could have said let Z sub T be 0, and then Z sub B would be negative 1.83, but that's maybe being unnecessarily silly about it. All right, so what can we cancel out? We can cancel out this term, the gamma Z sub B, because we've already said Z sub B is 0. Okay, so that's gone. Therefore, the pressure at B is P sub T plus gamma Z sub T minus delta X, density, acceleration in X. Okay, just moving things around algebraically. Our unknown is the pressure at B, which the pressure at T is 0, so 0 plus the unit weight is 6,600 newtons per meter cubed. Z sub T is 1.83 meters minus delta X is 6.1 meters. Density 672.8 kilograms per meter cubed. And now the acceleration in X is negative 3.05 meters per second squared. Now, just because I think it's interesting, I don't want to lump it all together in one step, but I want to I'm curious to know the individual contribution of each of these components that's adding to the pressure at B. So it's 12,078 pascals for the first grouping and 12,517 pascals from the second. Now let's look at that. The pressure at B is because of two things. It's partly because of the elevation difference between the 2 points, and then it's partly because of how the truck is moving side to side. So this first part, 6,600 newtons per meter cubed times 1.83 meters, this is kind of like it's just the hydrostatic equation. This is handling the elevation difference between the 2 points. But then the second component, the 12,517 pascals, that's the pressure difference between the 2 points because of the fact that the truck is decelerating. And so altogether, the cumulative pressure at B is the sum of those two. So it's 24,595 pascals. Do you have a question? The delta x is the distance between them in the x direction. So it's just only the 6.1 meters. Do you have a question?
Why did you add those 35
Yeah, it's because of the negative acceleration. Rachel? Yes? Yeah, so the only caution I'll give you against that approach is that if you have acceleration in two directions, if you start allowing yourself to think as, I'll just apply the hydrostatic equation anytime there's a vertical acceleration, that applies as long as the only vertical acceleration is just gravitational. But yes, you're right. We would have got the same thing by finding the pressure at A, which we already had over there, and then adding 1.83 meters multiplied by the unit weight of the fluid. Any final questions about that? Okay. All right. So here we had an acceleration, a local acceleration, meaning that the velocity of this truck was changing over time. So the fluid is experiencing unsteady conditions because the velocity is changing with respect to time. And Euler's equation tells us the response of unsteady conditions, how the fluid's pressure and elevation may be affected by that. Here's another illustration that makes use of Euler's equation. Let's say that we had water flowing through a horizontal pipe, and we wanted to accelerate the water in that pipe at 6 meters per second squared. So we're not talking about a convective acceleration. We're talking about we want the flow rate through the pipe to be increasing. And so what pressure gradient is needed to accelerate the water? Water moves through pipes because of pressure gradients. That's what drives flow, is the fact that in a pipe you have somewhere down the line where the pressure is low, and so the water is flowing through the pipe to get to that point of lower energy. So if we had a pipe like this, it's horizontally inclined, and we've got two locations where we've picked these points just so that we can answer the question about a pressure gradient. You know, the way to interpret that term, pressure gradient, is just what is the change in pressure, the incremental pressure over some incremental distance. And if we're talking about, you know, the SI system, then the incremental distance that would make sense for us to look at is, you know, 2 points that are a meter apart. You know, what's the pressure difference between the 2 points? And we're talking about water here, so we know the density and the unit weight of water. And here, the acceleration in the fluid is to the right at 6 meters per second squared. So that's defining the local acceleration that we're having to substitute in here. And if it's a horizontal pipe, then the L direction is the X direction. So this is similar, I think, to a homework problem that sometimes comes up, and I wanted to give you some exposure to the idea of a pressure gradient. Pressure gradients also occur during steady flow. Even if conditions aren't changing over time, it's a pressure gradient that's going to be driving flow when conditions are steady and uniform. But here the pressure gradient, we're assuming no frictional losses, and the pressure gradient is causing the flow to speed up. Okay, so right now location B is on the right side, so that's 2, so B is what we're going to be calling location 2, and A is location 1, because of the two, B has more x, meaning it's further to the right, and A has less x, meaning that it's further to the left. Euler's equation is going to be that the pressure at B plus gamma ZB minus the pressure at A minus gamma ZA is equal to negative delta x, the density and acceleration in x. And it's a horizontal pipe, which means that the elevations are equal to each other. Z sub B is equal to Z sub A. So it's just going to be a pressure difference between the 2 points. Since the Z sub B term and the Z sub A term cancel out, P sub B minus P sub A. And that is a pressure difference. And so the delta P and is equal to negative delta x, density and acceleration in x. So we can move this delta x to the left side of the equation and say that delta P divided by delta x is just negative density acceleration in x. And since this is water, that gives us a density of 1,000 kilograms per cubic meter. And the acceleration is 6 meters per second squared. And it's accelerating to the right, so we leave that as a positive value. So that means that the pressure gradient is going to be negative 6,000. And the units here, kilogram meter per second squared divided by meters cubed. And of course, a kilogram meter per second squared is a newton. So that's negative 6,000 newtons per meter cubed, which is the same as negative 6,000 pascals per meter, because a pascal is a newton per meter squared. So it's a unit of pressure. So as a gradient, that makes sense. We would expect the units of gradient to be pressure divided by distance, and that's what we have here. So the pressure would have to be every meter of distance between, as you move 1 meter through the pipe, the pressure is going to change by 6 kPa. And when that's the case, that means that the fluid is going to be accelerating through the pipe at 6 meters per second squared. So the main objective of this example is to give you another illustration of how Euler's equation can be used, but then it's also partly just to expose you to the idea of a pressure gradient. Any questions about that example? All right. Well, I know you're itching to put your calculator to some use. So here's how we're going to do it. I'd like you to work in groups of 2 or 3. Of course, if you prefer to go lone wolf on this, that's fine too. But I've got 2 examples, and for now I'd like you only to work on the one on the front. We'll talk a little bit about how to handle the one on the back after we've collectively looked at the solution for the first question. But in this first question, you can see that there is a tank, a rectangular tank of fluid that's accelerating both in the x direction and in the z direction. So from the signs, it's accelerating to the right and downward. And it's a tank of mercury, which is going to mean that the pressure changes a lot because it's such a dense fluid. And you should work it one location at a time. So first, we're going to break this up into 2 parts. The first thing, you need to find the pressure at F. And so you look the pressure at F is unknown, but the pressure at G is given. So that is the first step. You're looking at vertical. And so here is Euler's equation, sort of already expanded out in terms of the acceleration is in the vertical. So you'll see that I have, instead of delta x, I've got delta z as our incremental distance. And the acceleration is in the z direction. So the first problem is going to be in the vertical plane, and then once you've solved that, then the unknown actually isn't the pressure between G and H, because the pressure is given for both of them, but what's not known is how far apart they are, the delta x. But it will be the only unknown when you solve the second Euler's equation that I've written for you there on the screen. All right, so I'm going to stop talking and give you some time to solve for both of these. I've got the solution. I'm going to be circulating around, and so let me know if you've got any questions on it. Yep. That's what it is for room temperature water. Yeah. Just sort of the default standard. We've been using 9810 through this semester. That's not the correct distance, no.
Okay, the equation I can guarantee is correct.
What did you use as when you're talking about, well, let's see, did you find the pressure at F?
Yes.
Yeah, it looks like you've, 516, okay, no, that's right. That's a 5, right?
Yes.
Okay.
516,
Mm-hmm.
734.
Okay, so now in the x direction, location H is 2, right?
Right. Exactly. So it's here, 2 subtracted by 1, delta x is 1. So all of the numbers is right? And you rearrange the delta x.
Yeah, that's right.
Calculation wrong?
The acceleration is wrong. Yeah.
Yeah.
Okay, so any questions when it comes to calculating the pressure at F? Do you have a specific question? No? So what accounts for the pressure at F? So we start at the pressure at G, which we know is 485 kPa. And then it looks like there's a pressure increase and a pressure decrease. So one of them is because of the normal gravitational acceleration effect, and the other is because of the downward acceleration. And so the pressure at F would be bigger. The pressure at F would be bigger than the pressure at G because of the downward acceleration. So that's what this 147 is from. But then the pressure decrease, let's see, hold on a second. Yeah, the pressure decrease is because it's above it in elevation. So the Euler's equation accounts for both of those effects simultaneously. The normal gravitational acceleration, sort of hydrostatic thing, and then also the local acceleration that it's experiencing of 12.5 meters per second squared. And then when we look at the distance, trying to find the distance between the 2 points, here's what we do, is we rearrange Euler's equation to solve for delta x. And then we have to reconceive of what's location 2 and what's location 1, because now we're working in the horizontal axis rather than vertical. And so the location that's further to the right will be location 2, and that's H. and then g is location 1, and then the acceleration here, 15 meters per second squared. There should be a squared there. That's a little misprint there. Acceleration 15 meters per second squared. So when you go through the calculations, it should be 1.79. So I'll give you...
Would a problem like this be that easy, or would it be more complex?
Well, I just told you that this was an exam problem, and so it would be exactly this easy. But believe it or not, an easy problem like this sometimes can still trip the occasional student up. So they don't have to be any more complicated for this to identify who understands Euler's equation and who doesn't.
Can it be more complex than that?
And that's a matter of opinion, I guess. You'll get to see some more of the range of Euler problems when you work on the homework assignment. Euler's equation doesn't only talk about pressure differences, it also talks about elevation effects due to an acceleration. So here's a diagram that shows that. This is a figure that's presented in your book, and sometimes it throws people off because there's two liquid levels at the same time. So I just wanted to clarify that this is showing before acceleration, the liquid level was horizontal, and then during the acceleration, the liquid level is sloped. And so you can see that A prime, B prime is the liquid surface during the acceleration. And what this is showing is that the angle there is a function of how much acceleration there is. So if you're accelerating the tank to the right, the liquid level increases on the left. And that's similar to the rule I gave you earlier that pressure increases in the opposite direction of acceleration. You can say the same thing about liquid level. Liquid level increases in the opposite direction of acceleration. So here, the tank's accelerating to the right, and it's getting deeper as you move in the left direction through this body of water that we're analyzing. The pressure along the bottom of the tank is increasing. So the pressure at D is greater than the pressure at C when it's accelerating to the right. In the first case, when it's just motionless, the two pressures are equal. Pressure at C equals pressure at D. But when it's accelerating, the pressure at D is greater.
Would you give all three derivations in Euler's equation?
No. I'd only give you this. As the equation sheet, I'd give you this. So you have to sort of take that and then look at the picture or read the problem statement and try and think about, what is the L direction? Is it an acceleration vertically? Is it an acceleration in the X direction, and so on? All right, so the angle of this liquid level is a ratio of the acceleration in the X direction relative to gravitational acceleration. So you can calculate alpha using the tangent function, because if you know how much it's accelerating to the right, for instance, if the acceleration x is 9.81 meters per second squared, then that would give you a 45-degree angle, because the tangent of 45 degrees is 1, which is 9.81 divided by 9.81. And that's where this example comes in. We've got another truck carrying a liquid, but this time, instead of being enclosed like that very first example from the day was, this is open to the atmosphere. The truck is 18 feet long, and it has a bed depth of 7 feet. Now that's not the liquid depth, that's just how big the container is. What we know about this truck is that based on its brakes and based on the engine, it will never accelerate or decelerate more than 8.02 feet per second squared. And that's relevant because that's going to define the angle, like how much of an angle we can expect to see when it's accelerating. So what you're going to need to do in this example, it's on the flip side of the handout I gave you earlier, is calculate what's the maximum depth, the maximum liquid depth that you could fill this tank to without it spilling. Because if you filled it all the way, if you filled that to 7 feet, like when it's stationary, then as soon as it starts to accelerate, the liquid's going to spill. But if you put maybe one foot of liquid in it, then it can slosh around without spilling, but you could even fit more than 1 foot in it. So what I'd like you to do is use this ratio to calculate the angle, and then take a look at the geometry and try and see if you can calculate how deeply this tank can be filled without spilling when it's accelerating or decelerating. There are a couple of ways to handle this. If you find the angle, alpha, then you can find h that way by making use of the angle alpha. But you'll notice that what I said was that the ratio of h to 9 is the same as the ratio of the horizontal acceleration to g, because the liquid level would be horizontal if there was no acceleration in the x direction. And so how big h becomes is strictly because of the acceleration side to side. And if the acceleration was equal to g in the x direction, then h would be 9. And so it's a linear response to the acceleration it's experiencing in the x direction. All right, so let's take a look at these announcements before you go for the day. The homework assignment that's due a week from today, I would encourage you to get an early start on this Euler's equation stuff while you still remember how to assign 2 versus 1, how to handle the negative acceleration, you know, if it's to the left or if it's downward and so on. But those are just 4 problems, and we're going to begin talking about Bernoulli's equation when we have class on Thursday. So I'll see you then.